College students. This video is going to be called Spring 12, and it's the first video after the first test. So you've already probably taken the first test, and now this is where all the material that's covered in this lecture will be on test number 2. And we left off talking about seafloor spreading and how that led to plate tectonics. But we didn't talk about 1962 to 67. How did seafloor spreading lead to plate tectonics? It must be remembered that when Wegener originally came up with his theory of continental drift, it was not well accepted by the scientific community because he did not have a mechanism for how the continents could move that was feasible. 1962, Harry Hess and Robert Dietz introduced the theory of seafloor spreading, and what Hess and Dietz showed is that new seafloor is formed at the mid-ocean ridges. So let me have a picture for you here. Let me get you a picture of that. So let's take a good close look at seafloor spreading. Don't forget, seafloor spreading is from Harry Hess and Robert Dietz in 1962. We have already talked about this in some detail, but let me just show you one more time, because you have to understand this picture. This picture depicts Harry Hess and Robert Dietz's new theory of seafloor spreading in 1962. Shows that new seafloor is formed, and it rises in the gap between the mountains at the mid-ocean ridge, pushing apart seafloor away from the mid-ocean ridges. And when this mafic oceanic lithosphere, including the crust and the uppermost part of the mantle, comes into contact with the felsic continents, the mafic oceanic lithosphere subducts deeper into the earth. This can cause the continents to be pushed apart in this case. This continent towards the right and this one to the left, by the mafic seafloor pushing against the continents. And so the bottom line is the introduction of this theory of seafloor spreading, and if you don't get this, put it in your own words and rewatch the video, but it allowed for scientists to re-examine Wegener's idea of continental drift and say, wow, the continents can move, and this seafloor spreading is how they move. So imagine for a moment that we're not here in the year 2021, but we're in 1962. And scientists have been teaching about permanism. Probably 80-90% of scientists believed in permanism, that the continents cannot move. The oceans have always been the size they are today. The continents have always been in the positions that they are today. Now, all of a sudden, Hess and Dietz come out with this new theory of seafloor spreading, which says, you guys were all wrong. The continents can move, and Wegener's original idea was right. And the way they move is through seafloor spreading. Well, 1963, scientists basically said, they were mostly trained between, they were trained after World War II or between World War I and World War II, and they had been teaching permanism in their classroom. They're not going to just jump aboard and say, oh, everything I learned about in permanism was wrong, and now I accept Wegener's original idea. They're going to demand proof. And so scientists wanted to explore whether or not the continents were really moving or not, according to seafloor spreading. And the first thing they looked at was Earth's magnetic field. We have a magnetic field around our planet. And we have a magnetic North Pole near our geographic North Pole. and a magnetic south pole. Without getting into the heavy-duty physics of it, since this is an introductory class, I'll just tell you that around the turn of the last century, around 1900, I don't know the exact year, Faraday came up with an equation showing that the relationship between electricity and magnetism. And what he determined was that electrical fields produce magnetic fields. Electrical fields produce magnetic fields. Well, what is electricity? Electricity is simply a flow of electrons. And what the Earth's magnetic field tells us is that there must be some movement of electrons inside of the Earth. And this can only occur in a liquid, not in a solid. So that's one of the reasons why we know that the outer core is made of liquid iron. Otherwise, we wouldn't have a magnetic field around our planet. And the way the magnetic field works can be best imagined if you have a compass. If I take a compass out, the needle is going to point north, right? And Earth's magnetic field has been orientated so that magnetic north is where our compass is going to point. You know, if you go out and buy a compass, it's going to point north. Well, guess what, ladies and gentlemen? About 100,000 years ago, Earth's magnetic field was pointing south. So if you were there 100,000 years ago, your compass would have pointed south. 250,000 years ago, it would have pointed north. How do we know that? It's recorded in the rocks. The magnetic minerals in rocks point to the magnetic poles. And 500,000 years ago, the magnetic field would be pointing south. And what this means, ladies and gentlemen, is that when Earth's magnetic field is pointing north, we call those times of normal polarity. And I'm going to write that down so you can, because it's so important. So normal polarity means that Earth's magnetic field is pointing north, like it is today. 100,000 years ago, Earth's magnetic pole was to the south, so we call that a time of reverse polarity, where the magnetic minerals on the rock are pointing south 100,000 years ago, indicating that Earth's magnetic field was pointing south. So, when Earth's magnetic pole is north, we call that normal polarity. When Earth's magnetic pole is to the south, we call that reverse polarity. And we know in the past when we had normal polarity and reverse polarity by looking at the magnetic minerals in a rock. We can use this to test and see whether or not seafloor spreading is actually occurring. How can we do it? Well, let's go back to our seafloor spreading model again. If seafloor spreading is true, then we should see the rocks here where the magma is rising, the minerals should be pointing north, right? Because we're living in a time of normal polarity. And then later on, when Earth's magnetic field reverses itself, so it's south, then that would make rocks with minerals that are pointing south. And then it'll be north again. So if plate tectonics, if seafloor spreading is true, we should see stripes of igneous rock on both sides of the mid-ocean ridge, and those magnetic stripes should be symmetrical, the same on both sides, and the same thickness, and also parallel to the mid-ocean ridge. And the people who figured that out were two British scientists by the names of Matthew and Vine of Cambridge University. So they wanted to see, is seafloor spreading really occurring? If it is occurring, we should see magnetic stripes, normal and reverse polarity, symmetrical on both sides, parallel to the mid-ocean ridge. That's a tall order, if you ask me. Think about it. What's the likelihood of that occurring? Well, to their shock and surprise, they looked at the data from the seafloor, and we have stripes of normal and reverse polarity. So the darker colors are normal and the yellow is reverse, and they're symmetrical on both sides. Symmetrical means the same on both sides of the mid-ocean ridge, and they are parallel to the mid-ocean ridge. And this clearly shows that new oceanic lithosphere is being formed at the mid-ocean ridges and is moving away from the mid-ocean ridges like a conveyor belt, i.e., seafloor spreading is occurring. And if seafloor spreading is occurring, the continents must move. So the discovery of this really was almost the death knell of permanentism. But still, if we needed other ways to test and see if seafloor spreading is actually occurring. Now think about it. If new magma is rising at the mid-ocean ridges and the seafloor is spreading apart, like a conveyor belt moving in two different directions, would you expect to see older oceanic seafloor, or older seafloor at the mid-ocean ridges, or would you find older rocks farther away from the mid-ocean ridges? Think about that for a moment. Well, obviously, the youngest rocks form at the mid-ocean ridge. So if seafloor spreading is actually occurring, you should see older and older rocks as you move away from the mid-ocean ridges and go towards the deep ocean trenches. And the age of these rocks should be symmetrical and parallel to the mid-ocean ridges. In 1962 to 1967, scientists from JOIDES, what is JOIDES? JOIDES. JOIDES stands for the Joint Oceanographic International Development Exploratory Society. You don't need to memorize that, but it was set up during the Cold War when you had the communist world and the free world. And in the free world, our old enemies were now our allies. So Germany and Japan were our allies. And so Japan, the United States, Britain, France sent their ships into the Atlantic, the Pacific, and the Indian Ocean and sampled the bottom of the seafloor. And they wanted to see if seafloor spreading is actually occurring or not. Is it actually occurring or not? Well, let's take a look. Remember, if seafloor spreading is occurring, you should see younger rocks at the mid-ocean ridges and older rocks as you move away from the mid-ocean ridges. And the age of the rocks should be parallel to the mid-ocean ridges. Wow, look at this. To everybody's shock, it clearly showed the youngest rocks, which are in orange here, are around the mid-ocean ridges. And as you go away from the mid-ocean ridges, the rock's seafloor becomes older. And this change in age of the rocks is symmetrical and parallel to the mid-ocean ridges. See these green rocks that formed 60 to 90 million years ago? This band of rocks is parallel to the mid-ocean ridges. And this symmetrical pattern indicates that seafloor spreading must occur, if you think about it. Try and visualize it. So the paleomagnetic data, and paleo means ancient, the ancient magnetic data, and the seafloor age data clearly showed that seafloor spreading must occur. And so by 1967, when Tuzo Wilson came up with the plate tectonic theory by joining together seafloor spreading and continental drift, all of the geologists of the world, basically almost all of them, realized that plate tectonics is the best theory to describe how the Earth works. Why we have earthquakes, why we have volcanoes, and where we have volcanoes and earthquakes. Where can we find mineral resources? They're all around. And where can we find mountain ranges? They're all around the plate boundaries, the places where the plates meet. We can also study our geologic history by understanding plate tectonics. We have to know, for example, if we're going back 100 million years ago, where were the continents? Where were they 100 million years ago? Where were they 150 million years ago? Where were they 300 million years ago? Where were they 500 million years ago? We have to know how, where were the continents in the past and where did they go move to later on. So one last time, drilling into the seafloor shows oceanic crust is younger near the mid-ocean ridges and the older rocks are farther away from the mid-ocean ridges, exactly as predicted by the theory of seafloor spreading. Here you can see the magnetic stripes, exactly as predicted by seafloor spreading. Here you can see the age data. Younger rocks at the mid-ocean ridges in orange, older rocks as you move away from the mid-ocean ridge. And then they're symmetric. The age of the rocks is symmetrical on both sides and parallel to the mid-ocean ridges. Okay. So, now let's go beyond 1967, and we no longer have any doubt that plate tectonics is occurring because we have GPS, we have global position satellites, which can actually measure how fast the continents are moving and how fast the plates are moving. Here you can see the world's plates, the Eurasian plate, the North American plate, the African plate, the South American plate, the Indo-Australian plate. This little plate, here's the Philippines plate, here's the Cocos plate. So let's examine this diagram a little more careful. First of all, where you have two arrows moving apart, that's a mid-ocean ridge. And where you have two arrows going together, that's what we call a subduction zone. Where you have two arrows moving side by side, like right here in California, the San Andreas Fault, that's called a transform fault. So bottom line is, for your notes, you can write something like this. If the plates push together, we call that a convergent plate boundary because the plates converge. And when plates converge, you could get subduction. When plates pull apart, like at the mid-ocean ridges, we call that a divergent plate boundary. Plates pull apart, like at the mid-ocean ridge. That's called a divergent plate boundary. When plates slide next to one another, we call that a transform plate boundary. So those are your three kinds of plate boundaries: convergent, divergent, and transform plate boundary. Let's try and visualize that for a moment. This is a what type of plate boundary? A divergent plate boundary, such as at the mid-ocean ridges. What kind of plate boundary is this? Where plates push together. That's a convergent plate boundary. When plates slide next to each other, that's a transform plate boundary. Notice this subduction can occur at a convergent plate boundary. Okay, let's examine this diagram. Don't be intimidated by it. Here's your divergent plate boundaries where the arrows move away from one another. So there's a mid-ocean ridge here. There's a mid-ocean ridges here where new seafloor is being formed. Where you have these red triangles, those are subduction zones. Those are where you have deep ocean trenches, always marked subduction zones. And these numbers tell you how fast the plates are moving in centimeters per year. For example, the North American plate is being pushed towards the west at a rate of about 2.3 centimeters per year, which is about an inch a year. Eurasia, the continent of Europe and Asia, which is Eurasia, is moving away from North America towards the east at 2.3 centimeters per year. Now let me ask you a question. Which ocean is becoming wider? And which one is becoming more narrow? Well, North America is moving west and Eurasia are moving east. So the Atlantic Ocean is becoming wider every year by about 1 inch a year. And which ocean is becoming more narrow? The Pacific Ocean, because North America is moving towards the west. That might not seem like a lot to you, 2.3 centimeters a year or 1 inch a year. But think about 1,000,000 years. After 1,000,000 years, North America will move 1,000,000 inches towards Eurasia. So eventually, North America is going to collide with Japan, right? Some plates are moving faster. You can see here, you got measurements, 17.2 centimeters a year down here in South America. So South America and Eurasia are moving apart very fast. These red triangles, subduction zones. Where you have subduction zones, you have volcanoes, right? So where do we have volcanoes on the earth? Wherever subduction occurs. We have them in Italy, going all the way through Iran, in the Mediterranean. We have volcanoes along the edge of the Pacific Ocean, in the so-called Ring of Fire, all the way here from the west coast of South America, Central America, our Pacific Northwest, up here in the Aleutian Islands, off of Kamchatka Peninsula in Russia, here through Japan, all the way through Papua New Guinea, off of Australia, down here to New Zealand. Do you see how beautiful plate tectonics is? Now we know where we have volcanoes and where we have earthquakes. Earthquakes occur wherever there are plate boundaries. In other words, where there are these red lines. We have earthquakes because earthquakes are caused by stress, by rocks being pushed together, pulled apart like a divergent plate boundaries or sliding next to each other. Okay, we'll call that. I'll make another film later on.